gathered 500 people to compete in this one competition here at the Grand Line. We've narrowed it down to 3 best chemists, and they'll duke it out to see who's #1. These are the 3 things you need to compete and be the best there is in the business.
Brains, hard work, passion.
This is Hell's Chemlab.
Hello, I'm Ernest Rutherford, an English physicist in 1908. I'm most famous for my gold foil experiment, which discovered the nucleus of an atom and how there is positively charged particles within it. Hello, my name is Michael Faraday. I was born in 1791. I'm an English scientist who contributed in the fields of electrochemistry. I'm known for the discovery of benzene, and I also invented the oxidation numbers.
Hello, my name is John Dalton. I'm a chemist and physicist from 1766. My main contributions are theorizing that all matter is comprised of atoms and that atoms are indivisible. I also did some work with color blindness.
Alright, here on Hell's Chemlab, our first challenge for our competitors is for them to pick 2 of their favorite organic compounds and draw them out. We'll have them have 5 minutes to do this challenge, and then they will present them to me, the one and only, and we'll see who will come out on top. Let's find out.
3 minutes remaining. Alright, time's up. My first favorite compound is benzene. Benzene is my favorite compound because delocalization causes the electrons to be held together strongly, making it more stable and less reactive than an unsaturated hydrocarbon. My second molecule I drew is 1,3-benzyl-2-oxypropyl. I drew this, and this is my favorite because it has 2 functional benzene groups, and benzene is very cool.
Whoa, hold up.
Ow!
That's not the proper name. Everyone knows this is called benzophenone. As you can see here, we've got the first benzene group. In the middle, we've got a ketone, which is where the -one suffix comes from. And here we've got another benzene, which is where the phene comes from. Because as we all know, when benzene is a functional group, we use the word phenol, creating benzophenone.
Alright, so this is one of my favorite compounds. It is N-ethyl, N-methyl, 2-propylpentane, 1-amine. So this molecule is a 5-carbon main chain, which makes it a pentane. In the middle of this chain is an amine group, which is this nitrogen here. Off that nitrogen is a methyl and an ethyl. The 2-propyl comes from the second carbon off the main chain, right here, that has 3 carbons, which makes it the propyl. Alright, lastly is my second favorite organic compound, which is a 6-chloral, 1-phenyl, hexane, 1-ol. So to start off, it is 1-ol because of the alcohol located at the first of the main chain, and also off the main chain is the phenyl group, not the phenol, but the phenyl, which means a benzene ring off the main chain. And lastly, the chlorine, which is located at the end of the main chain. So yeah, hope you like it.
Alright, So what I drew is one of my personal favourites. I used to make this back in the day quite a bit when I was learning, but it's a part of me, so which is why I'm presenting it to you. What we've got here is 3-propyl, 4-cyclopropyl heptene. Now, right off the bat, we can see the double bond here, which means we use the -ene suffix, because as we all know, alkenes, double bonds, that's how it works. Now, what's interesting about this is that we've got a propyl here, which means there's 3 carbons, 1, 2, 3, but also another propyl over here with 3 carbons. So why cyclopropyl? Well, it's cyclopropyl because all the carbons are connected to each other and it's organized in sort of this circular form here. Now you may wonder, where did the numbers come from? Well, as we all know, we start the numbering closest to the double bond. That is what's highest on the priority chart as of now. Alright, so we've got it over here, 1, 2, 3 propyl, 4 cyclopropyl, heptene. That's one of my favourites. Alright, for my second compound, what I created was N-butyl, 3-ethyl, butyl amide. Now, let's get a closer look at this one because it really is quite interesting. First thing we notice is that I wrote it in this form. And what I want you to see here is the hydrogens and how they're distributed. And you can really see this double bond here, probably the most important part of the entire compound. Now, the compound ends with amide because of this amide here, which is a carbon double bonded to an oxygen but with a nitrogen here, as opposed to our common hydroxide group that goes with the carboxylic acid. Now, the way we named it, we say N-butyl because 1, 2, 3, 4 monkeys eat plenty of bananas. Alright, here's our butyl coming off of our N group. We start with that. Next, we've got 3-ethyl because 1, 2, 3, we have an ethyl group, 1, 2, on the 3rd carbon of the side chain. But what holds the key, it's the carbon that's double bonded to the oxygen, which means that this is the main chain, which is where butyl comes from because 1, 2, 3, 4, that's butane, so a butyl amide. This is really a great compound and I hope you enjoyed it, judges. Thank you.
Alright, for our second challenge here on Hell's Chem Lab, I will be assigning each competitor a monomer, and what they'll have to do is construct a polymer out of that. Let's see where this challenge takes these contestants and see what happens after our first elimination.
Alright, so for this challenge, I was given a dicarboxylic acid and a dihydroxyl and told to make a polymer. And so what I did was I used esterification, and in this process it released H2O. And this would not be able to form from 2 carboxylic acids because oxygen cannot be removed by the carboxylic acid, and this then forming a polyester.
For my polymer challenge, I was given one single monomer. The monomer is right here, called ethane, as we see by the 2 carbons and the double bond, ethene. So, I thought, how do you make a polymer from one monomer? Well, we've got at least a double bond right here in the middle, which means it meets the condition for addition polymerization. So, what do we need for that? We need our initiator. What we've done here is we've taken half of benzoyl peroxide, and when we split it in half, this bond between the oxygens split into 2 electrons, or the radicals that we have here. So, what we do, we now place the initiator in front of the first monomer. This electron now makes this bond unstable, these 5 bonds, meaning the double bond breaks. When this double bond breaks, one electron goes here, makes the full bond, the other electron goes over here. When it goes over here, it acts again as a radical, so that when the next monomer comes in, when we add it, hence the word addition, the same process happens over again, and only ends when we take another half of benzoyl peroxide and throw it in like that, which ends the chain. As we see here, we have 2 radicals, and the 2 radicals are what make the bond, and they are found here, in the middle, and over here. This is 2 repeating units. This is my polymerization. And this is my world.
How do you like the new haircut? I like it very much as well. For this challenge, I was challenged to create a polyamide, which is a condensation reaction between an amide and a carboxylic acid. So what happens here is no hydrogen is removed. The carboxylic acid and the amide are present, also with a dicarboxylic acid and a diamide, thus reacting this, and this right now, and creating this. Are you stupid? You idiot! Yes, this is a polyamide, and yes, it does contain a carboxylic acid and an amide, but hydrogen is lost, okay? And it's either a dicarboxylic acid and a diamide, or a monomer with a carboxylic acid and an amide. Not both, you idiot! How did you make it onto the show? Are you stupid, you incompetent fool? How silly of me. Of course. Of course I was wrong. Of course hydrogen is lost. How could I forget that, sir? That's what I totally meant to say. I'm extremely embarrassed with myself. Shut up, you idiot! That is not what you meant to say. I've had enough of your excuses, you incompetent fool. Get off of my stage right now and never come back. You are the first person voted off of Hell's Chemlab. Alright, so we're down to our last 2 contestants here, and we're gonna have them go in a one-on-one battle in this round. Now the challenge is, I give them both the same retrosynthesis reaction, and I give them 3 minutes to draw it out. Now what they have to do is, after the 3 minutes is up, whoever can explain the reaction to me the best wins the first season of Hell's Chemlab.
Yeah!
Alright, so we're here with one of our contestants here, John Dalton, and he is going to explain to us what he did in his retrosynthesis reaction.
Alright, so as we all know, we were given the compounds 2-butyl-3-fluoro-butyl-3-phenyl butanoate. And we had, from this large compound, track our way back to having an original benzene ring, as seen right here, and of course 2 alkenes. We could have gone alkanes, but we decided, because of the allotted time, we would go to alkenes. Now, how I did this. I began with the full molecule here. My first reaction that I decided to do, and actually, let me tell you a bit about my notification. This double-legged arrow here, that means a reverse reaction, as in, this is what it took to get this to this, and the name is what this reaction was. Alright, so, my first reverse reaction was esterification, a form of condensation that requires heat and acidic conditions, more specifically sulfuric acid H2SO4. Now, what this did here is, if I have a carboxylic acid on one side and an alcohol on the other side, I can take the H from the carboxylic acid and the hydroxyl from the alcohol, make water, and then have an ester in the middle, meaning there's a double bonded oxygen and then an oxygen in the middle of 2 carbons. A carbonyl group here. Alright, now, next what I did, I thought the easiest next thing to do was get benzene. So, from this here, I thought, how do I attach this chain to a benzene? That's simple, alkylation. But very important for alkylation is that we need an alkyl halide, which means we had this alkyl halide right here with a bromine where an oxygen would be. Now, we also had the catalyst of AlBr3, aluminum bromide, which is necessary in the reaction. Now from here, we have our lone benzene, and we have our alkyl halide. But we don't want an alkyl halide. So, what we did the reverse halogenation, which would require heat or UV to undergo. So, what that means now is that we have HBr as a product over here. We used bromine gas, Br2, and we added it to our organic compound. So now, what we've got is a very simple carboxylic acid. Now, from this carboxylic acid, what we decided to do was oxidize it, or the reverse oxidize, which means that it went from an aldehyde to a carboxylic acid by adding an oxygen. And the catalyst we used for this was KMNO4, one of the three we can use, which are KMNO4, H2O2, and K2Cr2O7. Alright, now from there we have our aldehyde. We think, what is the next step? We have to get rid of this double bonded O, which means we have to go back to when it was an alcohol. Now to go from an alcohol to an aldehyde, we have to oxidize it once again. So without using the same catalyst, we used H2O2. Now, from our alcohol, it's really quite simple. We simply hydrated an alkene to get to our alcohol. And that's what we're left with here, an alkene. But we're not done. No, we're not done. We have this large part of the molecule here that we did not deal with yet. So, let's start with the simplest reaction. We halogenated it to give us this fluoride component right here. So, after doing that, using heat or UV, we went, okay, now we've got an alcohol. How do we create an alcohol? Well, we can create one from an alkene, which is what we did using hydration. We used H2SO4, acidic conditions, and here we've got an alkene, and a benzene. And that is how you form this.
There you have it, folks. A stunning explanation by Mr. Dalton. And now we will move on to our second contestant, Mr. Faraday. Alright, now we're here with our last contestant, Michael Faraday. And we're about to hear what he did with his retrosynthesis reaction. Take it away, Michael.
Alright, so let's get this retro equation started. So we ended up with 2-butyl, 3-fluoro, butyl, 3-phenyl, butanoate. And so what we did was we took this alcohol, and to get to this we used esterification, which uses the catalyst heat and H2SO4. Now to get to this alcohol, we took the fluorinated alcohol and used hydrogenation, and that uses heat and temperature and pressure. Now to get to the fluorinated alcohol, we took an alkene and we dehydrated it, and that used heat and H2SO4. Now back over to here, to get back to this alcohol, we took the carboxylic acid and we alkylation.
Alright, well, I think we've heard enough from Michael Faraday. And after the break, you will hear who our contestant winner is. Later on Hell's Chem Lab. Alright, welcome back to Hell's Chem Lab. Now before the break, you saw both contestants draw out retrosynthesis reactions. Now both were done very well, but as you know, we can only have one winner on this show. And the resulting factor that made the one contestant lose was the fact that he couldn't say alkylation correctly. Are you freaking kidding me? Rutherford could have said that correctly, and he was an incompetent fool. Are you freaking mad? Now, without further ado, I'm pretty sure you know who this winner is, and his name, John Dalton.
Yeah! Yeah!
Alright, now that concludes this episode of Hell's Chem Lab. I hope you all enjoyed yourself, and until next time, we'll meet you all again right here on the Grand Line. Come aboard and bring along all your hopes and dreams.
Together we will find everything that we're looking for.